Great. Hi, everybody. Thank you for tuning in today. I'm super excited to introduce our seminar speaker this week, Dr. Edgard Rivera-Valentin, who is currently a staff scientist and NASA Early Career Fellow at the Lunar and Planetary Institute in Houston, Texas. Ed is a planetary scientist and astrobiologist, and I'm sure he would use a lot of other descriptors. But they have a very impressive range of expertise from remote sensing, data analysis, and numerical modeling, experimental work. Their research spans multiple planetary bodies from Mars to Iapetus. And of course, Ed loves brines. And so some of the work that they'll be talking to us about today is on brines. Prior to joining LPI, Ed received bachelor's degrees in physics and mathematics with a minor in planetary science from Alfred University, and a PhD in space and planetary sciences from the University of Arkansas, where they graduated in 2012. They proceeded to do a postdoc at Brown with Dr. Amy Barr for 2 years, and then Ed went back to their hometown of Arecibo, Puerto Rico, and joined the staff at the Arecibo Observatory as a planetary radar astronomer. You can see his background there, where they worked for 4 years until 2017, when Ed started the position at LPI. Outside of research, Ed is quite active in public engagement, diversity and inclusion activities, and is a tireless advocate for social justice. And I've known Ed for several years now, and they continue to inspire me. So I'm really happy that Ed took the time today to come and talk to us about their research today. And hopefully we're all going to learn a lot more about brines on Mars, I think. So Ed, take it away. Thank you so much for talking to us today. Thank you.
Yeah, apparently you can't. You have to unmic before you share. Okay. But now you can hear me and now you can see my slides, right? Awesome. All right. Thank you, Francis, for the introduction and for the invitation to talk to y'all. As the slide and the title suggests, I'm going to be talking about one of my favorite subjects, which is brines. And it's going to be specifically brines on Mars. How do they form? When are they stable? And then given the environment, what would be their physiochemistry? So how cold are they? How salty are they? And what does that mean for Mars's potential habitability? Before I begin, though, I want to give a shout out to several groups. So first of all, I'm sure y'all heard about Boricua Planeteers from Francis already, but we're on Twitter. We are a networking group for planetary scientists, astronomers, space scientists, and engineers from Puerto Rico. We try to increase the visibility of Latinx scientists and then also help out in terms of promoting planetary science, space sciences, astrobiology in Puerto Rico. So big shout out and a big whipa to the Boricua Planeteers. There's also the Planetary Scientists of Color. We typically meet up for DPS and LPSC, and we're also on Facebook. There's a photo of our meetup from the last time. I think this would have been the last time we met before chaos happened. So this was LPSC 2019. And we were actually able to meet up virtually for this LPSC. What was cool about that is in all the years that I've actually attended the meetups that are linked to DPS and LPSC, we typically have a group of 10, 15, maybe some 20 people at this virtual tag up. We were able to come up with 50 some odd people who joined us, which is super awesome. We were able to talk and figure out together how we want to move our group together. So we're actually putting to you an email list to help talk to each other. We've also, some of the members put together a Discord group. I look young, I know, but I'm a little too old, so I didn't even know what Discord was. But there's a Discord group where people are talking. But for the email list, I actually have a form that you can fill out to have your email and any social media that you have. And then that goes to only the people that have signed up for this list, so other planetary scientists of color. So if you're actually interested in having your name on this list and being able to be part of this group, please email me and I'll send you that form. And the other group I'll give a shout out to is Queers of Planetary Science. This is also a Facebook group. This is actually a hidden group. We want to make the identity of any student or scientist who is not out. So if you do want to be part of this group, you can also let me know and I can talk to one of the admins and they just send you an invite to come over. We also meet up for dinner at LPSC and talk. And then, so this specific talk, like I mentioned, is going to be about brines. And so on the subject of brines, I wanted to let everybody know that I am the lead organizer for the conference initiative called Brines Across the Solar System, which I hope all y'all attend every single one of these. And so some of you might know the part of the LPI's job is to put together conferences on behalf of the planetary science community. So sometimes scientists will come over, talk to the LPI to put together a specific conference, and it's their conference and we just help organize it. We also put together LPSC on behalf of NASA for the planetary science community. And we also put together conference initiatives. So these are multi-year conference series to organize the community around a central topic. So the last time we did this was a topic called First Billion Years, which centered around the processes that were active during the first billion years in the solar system. We had 4 conferences there. It was accretion, differentiation, impact bombardment, and the last one, which I got to convene, was habitability. So first billion years habitability, where we synthesized everything that we learned from those other conferences, the other 3 conferences, through the lens of how do those processes lead up to the habitable world we have today? What could this mean for other solar system objects, and what could this mean for other objects such as exoplanets? So this time around, the conference initiative is brines across the solar system. So we're centering around the process of brines. How do they form? Where are they stable? What do they mean for biology? Are they facilitating any prebiotic reactions? And are they habitable environments? So this one is a 3-part conference series. The first one actually happens this October. It's going to be called Modern Brine. So this is where are brines today and how do we know? And what does that mean for those bodies? What type of geological, geophysical processes and biological processes are they currently aiding in? And then Ancient Brines will happen next year, September 22. That one will hopefully be an on-site, in-person meeting, and it will have a field trip attached to it. Given the chaos that we're still living in, Modern Brines is expected to be a virtual conference. And then we ended the series with Future Brines. There, the idea is we're going to put together those knowledge gaps that we identified in those first 2 meetings. What do we need? What type of measurements do we need? What type of instrumentation do we need? What type of spacecraft do we need to really better understand brines as a process across the solar system? So that's going to be the main discussion for Future Brines. To learn more about the conference initiative, I have a QR code right here in the middle of the slide. So if you have an iPhone or I think on an Android, this also works. If you turn the camera on, it will auto detect the QR code and take you to the website. But if you don't have that handy, I actually have the link down here on the footer of my slide. So that's the web address. And you can go there to learn more about the conference initiative and learn more also about the upcoming Modern Brines conference. The abstracts for that will be due sometime this summer, so keep an eye out for that. And I hope to see everybody at these conferences. So now, without further ado, the main topic, brines on Mars, #water on Mars, right? The never-ending story. Before I go too deep into brines on Mars, I'm going to give a few caveats. So first of all, when I'm talking about liquids on Mars and brines on Mars, I am talking about bulk processes. So I'm talking about how these type of brines could form and how do they interact with the bulk environment? And then how does that come back to tell you what is the physiochemistry of these brines? So that does mean that I won't be talking about these niche environments, very smaller environments that maybe something is impeding that liquid from talking to the atmosphere or talking to the larger surrounding environment. Those can have different conditions. So for example, like brine inclusions in ice, that I won't be specifically talking about. Those need other types of tests to better understand. And I'm also going to be talking about superficial brines. So I'm talking about the formation of a liquid on the surface of Mars and in the regolith at the depth where the regolith is still in contact with the atmosphere. So that means I'm talking about 15 centimeters, depending on the thermal inertia, you could go down even about 0.5 meter, or so. This is where the thermal wave, the diurnal wave, is still talking to the regolith, where the regolith is still exchanging water vapor actively with the atmosphere. So I'm talking about those type of processes. Things that are deeper, like basal melting somewhere in the poles, or potential lakes in the poles. I'm not talking about that. Though as a person who does radar and does brines, if at the end of this talk you have a question about that potential lake in the South Pole, I'm more than happy to answer it. But the talk is concentrating on these superficial things. So back in my day, when we were talking about brines or talking about liquids on Mars, the data that we had was pretty much, meh, why are we going to talk about liquids? Today on Mars, there's a bunch of evidence that maybe there were lakes, there was rivers on Mars in the past, but maybe not today. Luckily, when I started grad school was right around the time period where we had seen this recent activity on the surface of Mars. So it was when goalies were identified as forming today. So the typical picture that's shown is this one here, where in 2001, there was this nice image of this crater wall. There's nothing on it. And then suddenly in 2005, there's something there. So there was a change, and when there's a change in a body where you think it's dead and there isn't much motion, then that's cool and that's interesting. And then when these processes or these features were looked at closer, people noticed that their morphologies were very similar to features that on Earth are typically dominated by liquids. So that is, these features had an alcove where all the sediments started to move away from, a channel where the flow velocity was high enough that the sediments were able to be suspended, and then a fan where now the flow velocity slowed down. No longer can you suspend these sediments and you deposit them out. So on Earth, these type of things typically require a lot of water to move all of this around. And so when these were first observed, it was, yay, water on Mars. I think probably maybe the first hashtag water on Mars. But as we continued studying these processes, specifically recent activity for goalies, what we found out is that they're primarily occurring during the wintertime on Mars. And so given the environmental conditions there, they are probably not related to liquid formation. What they're probably related to is frost. There's a paper that was published just a few months ago, revisiting all of this, looking at the temporal aspect and also adding in identification of frost formation as it relates to these features. And it was further evidence that it's probably you're having frost forming in the regolith at nighttime, during the daytime. As that frost volatilizes back into the atmosphere, that sudden phase change is enough to instigate the motion of these features. So after we've studied these, they inspired the idea of, hey, maybe liquids on Mars, and then, oh no, no liquids. And then we kept going back and forth. There was dark slope streaks. There were a bunch of other things that have been observed that went, oh, liquids, and then nope, never mind. And I think the one that stuck around the longest was recurrent slope lineae, RSLs. So these are features that the temporal aspect of it is they're forming during spring and summer. They're forming on the part of the crater wall that is facing the equator. So that means that they're getting the most intense heat. And they lengthen and darken over time, then they fade back to the background temperature, background colors. So a lot of the properties of these features really will, at first, when they were discovered, pretty much towards the end of my grad school time, really said, hey, maybe these are evidence of brine formation on Mars today. Now, of course, the most recent literature that we have either suggests that these are fully dry processes, so just fully dry mass wasting processes, or they might be instigated by some sort of liquid formation, but not dominated by liquids. Either way, the observation of these features that at least initially suggested liquids could form on Mars today launched very deep experiments, right? A bunch of people started having Mars simulation chambers, really studying, okay, can this liquid be stable on Mars? What other processes can lead to the formation of liquids on Mars? What type of brines could be stable? So it really launched this nice set of bunch of years and a bunch of really nice literature looking at better understanding stability of brines on Mars. Because when we first started talking about can you even have a liquid on Mars, we looked at it from this very fuzzy process, and that is you put everything on a phase diagram that we're used to, so temperature and atmospheric pressure. And so on this blue line, you're seeing the typical conditions on Earth. And you see, okay, Earth can see ice, it can see liquid, and you can see vapor in the atmosphere. Cool. And if we put the conditions on Mars, we see that most of the water should be in the ice phase. Some of it can be in the vapor phase, and there's this little tiny itty bitty section there that could be liquid. The idea was, okay, if there's a liquid, the conditions would mean that these are very transient events. They might happen for a few seconds or a few hours, but these aren't really bulk processes. But it turns out that this is, like I mentioned, a rather fuzzy view into can a liquid be stable? Because on Mars, you are hyper arid conditions. You are extraordinarily dry, drier than the driest place on Earth. You are super duper dry. I need to stress that because it's so dry. And throughout this talk, I'm going to start comparing the conditions on Mars in terms of the atmosphere and how dry it is to other places on Earth to really convey this message. It's important. When you're talking about that level of dryness, you have to add another aspect to better understand whether a liquid can be stable on Mars, and that aspect is evaporation. So the current global circulation models that we have, like Mars WRF, Mars Weather Research Forecasting, what I did is I took that and I checked, okay, across Mars, what is the total amount of water vapor that can exist in the atmosphere, the maximum and the minimum? Turns out that that simulation would suggest that you can go from 0 to about 10 pascals worth of water vapor at the surface. To compare the measurements that we have from the Phoenix lander and the Mars Science Laboratory, which are two spacecraft that we sent to Mars that actually have meteorological packages and can tell us something about the near surface water vapor, those max out at about 2 pascals worth of water vapor. And as another reference, the driest place on Earth can get, the driest it typically gets is something like about 100 pascals of water. So just to put these numbers into reference in your mind. So what I did is I took that GCM and I said, okay, how many hours are these conditions actually occurring on Mars? Is it something like where we're used to on Earth that for every single amount of water vapor we have, it can experience every single temperature range that we have on Earth? It turns out that's not the case. And we've been seeing this with all of the instruments that we have, Phoenix and MSL, that temperature and water vapor are very much correlated with each other. When one goes up, the other goes down. So on Mars, what you'll see is the typical water vapor is something like less than about 0.5 pascals for the temperature range that I have here. And whenever you reach this 10 pascals, that only happens for a very limited time and temperature range. I did forget to mention these colors are the number of hours these conditions occur. It's just the log of that. And the reason the plot doesn't look super continuous is I had binned it to do all of these counts because it's a lot of data. And you see that when you go up to higher values of water vapor, that's really only occurring for a very limited range of temperatures. So given this, if we go back to that previous plot I had shown you the phase diagram and the little tiny sliver when it said, hey, maybe this liquid could be there because it won't be frozen or it won't be boiling. If you put in the added stability criteria of let's make sure you're not really quickly evaporating away, well, at that temperature where we saw liquid could form, the vapor pressure just above the liquid was 600 pascals. So let me define vapor pressure for those of you who don't know. So every liquid, every now and then, one of the molecules inside the liquid has enough energy that it escapes the liquid and comes up into the vapor phase just above it, and then it just goes back down. So the amount of molecules that are above that vapor or above that liquid is temperature dependent. So the higher the temperature, the higher we call the saturation vapor pressure. Lower the temperature, the lower that pressure. So when you're evaporating away this liquid, you're actually evaporating away from this vapor just above the liquid. So the liquid goes to vapor and then goes up into the atmosphere. So with that definition in mind, these liquids would have a saturation vapor pressure of about 600 pascals. They are evaporating into an atmosphere that at most would have had 10 pascals, but typically it's 2 pascals. Evaporation is controlled by 2 things, temperature and the concentration gradient, how much you have here and how much you have in the atmosphere. So whenever that gradient is so drastic by several orders of magnitude, your liquid will quickly evaporate away. So even though it may not be frozen, it may not be boiling, you're going to lose it really quickly. In this case, you would lose it on the order of just a few seconds. So when you're talking about just pure liquid water, it's kind of difficult to get it stable on the surface of Mars. So that's why we end up having to talk about brines. Brines are cool because when you add salts to a liquid, it does 2 important things. First of all, when you add the salt into the water, salts then combine over with the water molecules. And then when the liquid wants to go to freeze, water, when it freezes, actually likes to, so you all know probably that water molecules are polar molecules, right? So one side's more negative than the other. When it goes to freeze, it likes to line up plus, minus, plus, minus, plus, minus. When salts combine then with the water molecule, and that molecule then goes, oh, I'm going to freeze, it kind of just bounces around because it's not coming in with a charge. So that drops the freezing temperature of the liquid because now you can have the molecule more free. The other thing that it does is because you've now bonded this molecule to the salt, you've also reduced that vapor pressure because now you're not having this molecule jumping up into the vapor phase. Only those free water molecules are jumping up into that vapor phase. So because you reduce the vapor phase above the liquid, you reduce the evaporation rate, right? Because you've now made it less, so it's closer to whatever is in the atmosphere, and you've also changed the boiling point or the boiling temperature. So brines are cool because you're fighting off the processes that are trying to actively get rid of you being in a liquid. Now, when you're talking about brines, one of the parameters that helps us better link that brines chemistry back over to the environment is something called water activity. By the way, you'll probably end up hearing my dog at one point or another bark and walk in the room and shake. I like to do that while I'm talking. So, water activity. So here I'm going to pause for a second because I'm going to be talking a lot about this parameter. And I'm going to be showing you a lot about this, so I want to make sure I define it well. So water activity is a measure of how many of those free water molecules you now have that are not bonded over with a salt. One of the ways of measuring it is you measure the amount of water molecules that are in the vapor phase, right? Because like I mentioned, the more salts it has, the less molecules are going up into that vapor phase. And all you do is you take that amount of molecules that are in the vapor phase and compare it to how much it would be if it was pure liquid water. So water activity, if it didn't have any salts inside of it, the amount of molecules in the vapor phase should equal the amount that is in saturation. So an activity of 1 is pure liquid water. And if the salts are bonded with all of the water that's ever in this liquid, then there's no free molecules in the pressure in the vapor phase. Your activity is 0. Now, if this liquid is in equilibrium with the atmosphere, so it's no longer evaporating, that would happen because the amount of molecules in that vapor phase above the brine is close to or exactly the amount of molecules that are floating around the atmosphere. So you reduce that concentration gradient to 0, so you're no longer evaporating. Because of the way this parameter is defined, that would mean that activity, the water activity, is related to the relative humidity with respect to liquid. So if we measure relative humidity with respect to liquid, we can then know something about what would be the water activity of this stable brine. Now, this isn't magic. This isn't something that we just use in physics and say, look, let's just assume a spherical cow and go forward. This is actually something that helps us out in food. When you're transporting food from one place to the other and you want to make sure that it doesn't have microbes growing all over it or fungus growing on it, you want to make sure that it gets to the grocery store happy-go-lucky. What people do is they actually put these in containers where they control the humidity inside of the container. right? And by controlling the relative humidity inside of the container, they're controlling the water activity of any liquids that would end up forming on any of these foods. And because microbes can only tolerate a certain amount of water activity, then you are able to stop some of these things growing on your foods. So this isn't something super weird. This is something that we actually use here on Earth. So now having this idea in mind of what water activity is, now let's go back to the effects of salts and start understanding what this could mean for stability of brines on Mars. So here's one way we could look at it. If we consider pure water on Mars at the typical temperature, at 273 Kelvin at the typical atmospheric pressure, if a pure liquid water forms, it would either instantly freeze, instantly boil away, but if anything, you're evaporating pretty quickly. And so I know here you'll see millimeters and you'll go, oh, well, that's really slow. Remember that if you collapsed all of the water vapor on Mars, you would only create a thin micron amount of water on the surface, about tens of microns on the surface. Okay, but now let's say we added salts. So we reduced the water activity to 0.9. Because we reduced the water activity, reduce the amount of molecules, free water molecules in the vapor. So concentration gradient goes down, we reduce the evaporation rate. Lower water activity means lower freezing temperatures. So now this thing can stay liquid down to 263 Kelvin. And it also means that it can avoid boiling up to 275 Kelvin. So we increased the range that this liquid would be stable on Mars. If you go all the way down to a water activity of about 0.53, which is what's called the eutectic water activity for calcium perchlorate, here, for those of you who don't know, eutectic water activity is the lowest water activity that this liquid would have before the salts precipitate out of the liquid. Okay, so this would be the lowest water activity that you could have in a calcium perchlorate brine. You reduce the freezing temperature down to 198 Kelvin, you're evaporating even slower, and you increase the boiling temperature up to 282 Kelvin. So you can see how quickly you can start increasing the range of conditions that you can have these liquids stable on Mars. That's why brines are cool. But now we can take this idea that we have for a parameter that's describing a chemistry aspect of these brines. As I mentioned, that we can relate this to the humidity on Mars. So we can take this number and we can take what we learned from this and now start comparing this back to what we know about Mars and the conditions on Mars. So that's what you're going to see in this diagram, right? So remember, on Mars, there's only a certain combination of temperatures and water vapors that can happen in the atmosphere. And those conditions can be typically well described as being inside this triangle. This black triangle that I have on this graph on your left side is the cyan triangle that you're seeing now on the larger graph, where again, we have temperature on the x-axis and water vapor pressure on the y-axis. What I've done here is that in color, I'm showing you the water activity of a brine. What is the water activity that a brine needs in order to be stable at that temperature and vapor pressure conditions? So you're not freezing, so you're not boiling, and you're reducing your evaporation rates. This blue line that you see here, that's the relative humidity with respect to ice. So this is where ice should start forming. It is not necessarily where you completely freeze your brine out. That's just where ice starts to form. You can stay and continue to have some liquids until you reach that eutectic temperature, so that lowest temperature that this liquid could be stable at. In this case, I'm just showing you the eutectic of calcium perchlorate at 198 Kelvin. So beyond 198 Kelvin, your ice. Between the dashed line and the blue line, you could have ice and brine. And beyond the blue line, you could have a liquid. It's just that that liquid would need to have these water activities. So what we're seeing here is that the most stable water activity that these brines could have would be about 0.66. And at these higher temperatures, you start quickly going into what's colored in this graph as black, which means the water activity is zero. Like you just have salt. We're not talking about a liquid anymore. You just have salts. So there's only a very restricted range inside of this plot where you could have a stable brine. Okay, Now, this is a very bulk view of what one could expect about the conditions of brines on Mars. And now I'm going to take it further and just complicate it a few extra steps. Okay. The first complication I'm going to do is let's look at now what processes can lead to forming a brine on Mars. All right. We can talk about melting of ice. So if you have an ice table and you have salts next to it and you melt the ice, that'll lead to a brine. What type of conditions would you consider, or what type of conditions could that brine have? The process that I find most interesting is called deliquescence. So in deliquescence, you can have, if you have a salt exposed to an atmosphere, if it's a hygroscopic salt, every now and then water molecules in the atmosphere are hitting that salt and they end up being adsorbed onto the salt. And at a certain humidity, so once that salt has adsorbed enough water around it, it actually just goes into solution. So that's the process we call deliquescence. So you'll suddenly form a liquid there. And that liquid will stay until you reach what's called the efflorescence. So that's the point where that salt gives up all the water and it goes back away. I'm going to show you a video here in the screen that hopefully works over having a virtual talk. But this video is of deliquescence happening in the lab at the University of Arkansas. This was taken by my friend and colleague, Jennifer Hanley, who's currently working at the Lowell Observatory. So in these experiments that were part of her dissertation, she was looking at the stability of deliquescence. She was really trying to understand when it occurs and when this liquid would effloresce back out. So you're going to see a video of deliquescence actually occurring. And what you'll see at first is everything's white because it's the salt, and then you'll slowly see things going into solution and clearing up. That's actually that liquid forming. Okay, so we start off with a bunch of things that were white, and as time goes on, you're seeing all of that disappear, and you see these things going into solution. You're seeing liquid forming. This is taking a while, right? So this is over a couple of hours. It's here only a few seconds, but it's actually a couple of hours process. But pretty much deliquescence is a quote unquote instantaneous process. That is, the moment you reach the right conditions, one of these salts somewhere will deliquesce. It just takes a while for the entire thing to deliquesce, which is what this type of experiment shows. You immediately form liquids at the right conditions, and then it just took a while for everything to go into liquid. Okay, so with all the experiments that Jen had done and the other people at the University of Colorado Boulder and University of Michigan, we have a good phase diagram to understand when one could expect this process to occur. So this talk is going to have a bunch of these phase diagrams, so I'm going to slowly walk us through this one. So again, we have in this case, we have water activity on the x-axis and temperature on the y-axis. This black line you see here, that's relative humidity with respect to ice when that reaches 100%. So this is the ice line. This is where we would expect ice to form. This blue line is the deliquescence relative humidity. So this is where deliquescence would start to occur. So anything between this black line and this blue line, one should expect there to be a liquid, and we would call that a stable liquid. Now, from just pure physics perspective, what would happen is if you have the conditions inside here and then suddenly the humidity starts to drop, and so you start moving this way in the diagram and you pass the blue line, from a pure physics perspective, you would expect then, once you pass the blue line again, to immediately give up your water and go back into just salt and water vapor in the atmosphere. And now the other version of this is if you cross the black line, from physics idea is that you would immediately just freeze out. However, through all of these experiments, what we're finding is that kinetics is important. Kinetics being the time it takes for these changes to occur. So what we found is that once you pass the blue line, you are still liquid. You have to wait until you pass this red line, which is called the efflorescence relative humidity, so that then you've reached the conditions where it's so bad that you fully give up all of your water vapor. But you are still a liquid between the blue and the red. Same thing goes on the other side. You actually have to wait till much higher relative humidities or much higher water activities to fully freeze out. So between the black line and the cyan line, you have ice brine, so you have the slushy. You have to pass the cyan line until you finally just have ice. So the cool thing when you're talking about deliquescence is that all of these experiments have shown us it is a broad field, right? Everything that you see here in gray are conditions that would support liquid forming on Mars, as long as you pass this blue line first. So we call everything in this gray area the stable because that's what physics had told us to expect. And these grays is what we call metastable. These aren't expected quite by thermodynamics, but we're seeing it occur in the lab and we're trying to explain it by kinetics. So because we have now this phase diagram and we have collected this beautiful data set from both Phoenix and MSL, and now up and coming Mars 2020, we're then able to understand, can this process happen on Mars today? So here I'm showing you Phoenix data from the TECP, Thermoelectrical Conductivity Probe. In the purple color, you're seeing just the raw data outputs. And in the magenta color, you are seeing the data as it was hourly average. But you can quickly see that there are definitely time periods here where the measured humidity and the measured temperatures were within this stable liquid area. So that means once we cross this blue line, or even if you cross it from the other side, if you cross it from the black line, anytime you're inside here, you have a liquid, right? So Phoenix, the conditions tell us, yes, you should definitely be able to be forming this type of liquid on Mars through deliquescence, as long as you have calcium perchlorate there, and all the measurements we have were suggesting that there should be perchlorates there. As an example of a diurnal curve, here is one of the days. Now this day didn't have data across all of the hours, so you do see a little jump here and not back, so it's not a full circle. But what happens is, so here's about 1 a.m., and then it starts, humidity starts to decrease. As it gets a little bit colder, you reach your maximum humidity around about 4 a.m. local time. Then the sun starts to pop up, your temperature goes up, you're crossing up here, you're above now the eutectic. So that's the first thing that you need. You want to make sure you're above that eutectic temperature. And then if you keep going, once I pass the black line, bam, I am a liquid now. I'm above the eutectic, I'm within the liquid phase. I can now have liquid forming. And again, the experiments have shown us that I have to keep walking along and wait until I'm past the red line to give up everything. So for all of these hours, I can have a liquid on Mars at the Phoenix landing site. That's super cool. So at the polar regions where Phoenix landed, this process seems to be feasible. How about at MSL, so Gale Crater? So here's the data from the Rover Environmental Monitoring Station, the REMS, that MSL has. And it's kind of sad, right? So, okay, so at the equator, maybe you're not forming liquids because you're really far away from there. Or can you? So here's where we have to remember that all of these instruments that we sent to Mars have actually large error bars. Every time they measure something, the error bars are rather big. And sometimes they give you unreasonable numbers. So these measurements are actually not confident when you are at low humidities. At that point, you can even start getting negative values. So unless someone has invented a vapor pressure black hole on Mars that is giving you something negative, I don't know how you would do that. And sometimes it'll even give you humidities up to like 800%. Obviously, these are not real. The error bars are really, really large. So one of the first things I did in a paper that I published in JDR Planets was I cleaned up the data and only showed the more confident values. And I started looking at, okay, with an error, can any of these data points actually be in the liquid phase? That's what we have here. After I cleaned up the data, this is the only data that is then left from that beautiful cloud that you saw. This is the only ones that were confident. Now, of those confident data points, there's these two ones that with an error, which is being represented by the box. So this magenta point and this magenta box is actually the error bars around this point. Same thing with purple here. This purple point and this purple box is where this data point can actually exist, given the errors on these measurements. So these two ones can actually be in the liquid phase. And these will occur at Sol 1232 and 1311 during the morning and late evenings. And during active sand dunes. So when the rover was over sand dunes, low thermal inertia terrain. To show you what that looks like, this is on Sol 1232, a nice context image that the rover took, and you're looking out, looks like a beach. You can kind of expect somewhere a nice ocean. You can imagine me on a chair sipping a mojito, like totally enjoying this, looking down and going, okay, where's my Deliquescence salts? Prove me right, prove me right. And then, you know, you're gonna sit there for a while with a spacesuit waiting for that. Now, the next thing I'm actually showing you is then, okay, with all this data, let's look at what happens when this water vapor and this temperature is going through the sand, right? Because sand is very porous. So that sand is gonna breathe in and breathe out water vapor. So where at depth can this be occurring so that we can tell MSL, hey, when you're over these type of terrains, maybe stop and take extra data and stop and look around more to see if this process is happening. So that's what I did here. So we're seeing thermal inertia on the x-axis and albedo on the y-axis. For every one of these combinations, what I did is I plugged everything in and I measured, or rather I simulated what the conditions in the subsurface would be. And I waited for when the temperatures and humidity was just right to allow for deliquescence to happen, and then I started counting up the hours. This black area here, those are combinations of thermal inertia and albedo at Gale Crater that would not allow deliquescence to happen on the surface or even the subsurface. Once you get into these red zones, that's where we're talking about combinations of these parameters that would allow for deliquescence to happen. Now, not all of these happen within Gale Crater, or rather the combination of these do not happen on Gale Crater. So these white dots are the combination of these parameters that the rover has actually trekked across. And you'll see that most of these combinations, you know, they're all in the black zone, so no deliquescence should be expected, except this one dot right over here, which happens for a thermal inertia of 180 and albedo 0.11, which turns out to be really close to the values of the terrain the rover was over on Sol 1232. So we went from the data that REMS took on that day saying maybe with an error you could have deliquescence, to the simulation of the subsurface saying, yes, you might be able to have deliquescence occurring somewhere down to like 5 centimeters or a few in the subsurface. So these are snapshots. What I've been showing you are snapshots of these two different areas of Mars, right? But remember, we have this GCM, global circulation model, that lets us know something about the global aspect of weather on Mars that has been informed by these instruments, has been informed by instruments that are flying across or orbiting Mars. So it's reliable now to the point that we can take that data and start to figure out where can we expect this process to happen across Mars. So that was the topic of a paper I published in Nature Astronomy just last year. So what you're seeing here is a map of Mars, and over on top of it, I've overlaid in color the percent of the year you could expect deliquescence to allow you to have a solution on Mars, so having a brine on Mars. So you see that once you get closer to the poles, just like Phoenix taught us, it is easier to form brines there, right? But you can start forming brines even down to closer to the equator, just because of local topography and what have you. So cool. So deliquescence looks to be, from the in situ data we have, from the global circulation models we have, it looks to be a process that may allow us to get to a brine on Mars. But with all this data, now let's start looking over into, we answered, can there be brines, stable brines? Now we need to start looking at the aspect of what type of chemistry should we be expecting. So to start doing that, we can go back to that phase diagram and compare it back over to the environmental conditions we have on Mars, right? So these different lines you see here, these are the lines that would allow us to form a brine of calcium perchlorate, magnesium perchlorate, or sodium chlorate, okay? So just like we did when we were going through MSL and Phoenix data, we want to make sure we're between the blue line and the line that's representing the salts. So here what I've done is I put dashed lines representing isobars. So these are lines of constant water vapor pressure. And you see that, so remember at the beginning of the talk, I mentioned that MSL and Phoenix both measured about a maximum of about 2 pascals worth of water vapor. So if you follow this 1 Pascal line, you'd see, okay, cool. The measurements that we have from Phoenix MSL do tell us that calcium perchlorate could form and magnesium perchlorate could form. And as I mentioned, the GCM says that you can go all the way up to 10 pascals. So cool, let's go this way again. So yep, calcium perchlorate, yep, magnesium perchlorate, and that's it. So because we have this data, we can now go, okay, we probably can't form a brine with sodium chloride, but we can get to magnesium and calcium. So that means that we can, looking at where this isobar touches the blue line, we can start using that to guide us to understand what is the best case scenario for the types of brines that we could form on Mars. This tells us that the type of brine would need to have a eutectic temperature of less than 230 Kelvin, no eutectic water activity of less than 0.66. Let's complicate this, all right? Remember, there's only a certain amount of conditions that can actually occur together. So only a certain combination of temperature and water vapor pressure, right? Remember that plot I had shown you at the beginning, only certain combination of vapor pressures and temperature occur on Mars because it's that hyper-arid. So we can't expect that this 10 pascals happening at 230 Kelvin, right? 10 pascals is actually looking over here at being higher than 230. So that combination is not doable. So now let's take that GCM, let's give it a range of water activities across Mars and then see where suddenly a brine with that given water activity can avoid freezing, boiling, and evaporating. So that was the topic of another paper that we published in 2020 in the Planetary Science Journal. And here are maps that are showing for the range of water activities that's something that started allowing to have a brine on Mars. So actually we had to go all the way down to 0.55 to allow somewhere on the map to have a stable brine. So at an activity of 0.55, that gets you eutectic temperature of 205 Kelvin. So we had to go lower once you started to consider the environment and those relevant combinations. And then the lower the water activity, the more stable that brine would be across the surface of Mars, like I had mentioned in the beginning. So great, we've shown that according to the experiments we have and how they've told us these liquids could form in terms of deliquescence, in terms of melting, and then putting that together with in situ environmental data and GCMs, we put all of that together and said, okay, a brine can form on Mars, and given these combinations, we've now also found what type of chemistries and what type of temperatures would allow these brines to be stable. Now we've gotten to the point of the talk where we can put everything together into what could this mean for life. For that aspect, there's actually law, or not law per se, it's policy, it's international policy that defines what a special region on Mars is. And that is an environment that can host liquid water that meets or surpasses certain temperature and water activities that would allow known terrestrial organisms to replicate. So this takes into account the temperature and water activity tolerances of known microorganisms on Earth, and says, okay, so if we're the lowest metabolism that has been seen is something like 255 Kelvin, and the theoretical lower limit for water activity is 0.6. So we can put this together and say, so if you have a brine anywhere that is a temperature higher than 250 and higher than and water activity higher than 0.6, we call it special because Earth life would be okay there. Okay, so if we start from this framework, let's compare this framework over to what we know of Mars. So on this plot, what I've done is in the cyan region, you're seeing all of the possible combinations of relative humidity with respect to liquid and temperature that can happen on Mars. The blue lines are just bounding the maximum and the minimums, okay? And again, I have isobars, which are the gray lines going across it. In green, I have what we call special region. So water activity of 0.6 and temperature of 255 Kelvin. And the first thing that you should notice is that we're talking about needing water vapor pressures of 100 pascals, 1,000 pascals. And on Mars, you just ain't gonna have that. Remember, the maximum is 10 pascals, and that's only occurring at these higher temperatures. Typically, it's closer to less than the 1 pascal. So we're showing that the type of brines that one could expect to be stable on Mars are really far away from the special region. We also have this thing called uncertain region, and even there, we're really far away from this. But let's put this into a little bit more environmental context and understand, how about the Earth analogs we have and what are they telling us? So on this plot, I have these uncertain region highlighted again in yellow. In the magenta, we have the Phoenix data, and then the purple, we have the MSL data, so you can see where they fit within the range of possible conditions of Mars. And then this bluish region, I have the Antarctic dry valleys, so they have a meteorological station at Taylor Valley, which I then took that data from, and then also data from the Atacama Desert. So both of these places end up being able to produce brines that at one point or another would be uncertain or would be even really a special region. So these areas do end up going into time periods where you could have a habitable liquid. But they do go also into regions that wouldn't be habitable. But we know that these places, that there is life there, right? Alfonso Davila has done really cool work looking at endolithic microorganisms that are inside rocks that are using deliquescence to survive. So still kind of far away though, right? In terms of the Antarctic dry valleys in the Atacama Desert, we're still really far away in terms of Mars compared to these places. Mars is much, much drier. It's a much harsher place to try to survive against. Now, these special regions and whatnot, those limits, you know, we're constantly exploring new life on Earth and constantly exploring these new environments and what they have to tell us. So after those papers were published, there's actually newer discoveries that came along. So first of all, when those papers were published, we had this idea that the theoretical lower limit of water activity was at 0.6. And so I'm putting that now in the solid black line here and giving you the citation. There's also work that has amassed a lot of the temperature, or rather metabolic rates as a function of temperature, and tried to extrapolate across different organisms what would be the theoretical lower temperature limit where that you could still have an organism happy-go-lucky. So that comes out to be 233 Kelvin. So that's this line, black line right here that I've drawn. Okay, since that special regions paper has published, there's been a bunch of other discoveries. So first of all, deep sea brines in the Mediterranean were found to actually be happy at high temperatures, but at really low water activities of 0.4. So this, in 2018, just a few years after the publication of what should be the lower limit in terms of water activity, we found something surviving at far lower water activities. However, when we went to Don Juan Pond and have been looking there, we're seeing that the temperatures there, which are really close to that 233 Kelvin value, are also really low. Water activity is about 0.45, maybe even down to 0.26. This is not, we haven't found convincing evidence that there is something living in the Don Juan Pond. So this is dead, but this is alive. So maybe the multiple stressors of being extra cold and extra salty aren't good there. Early in 2020, there was also these experiments for methanogens using deliquescence. And those 2 points are here in their experiments where they showed that you can have a methanogen dry out, but then the moment there was deliquescence, it would come back to life. But the temperature and humidity conditions of those experiments were all the way up here, actually in the special region zone. So this isn't showing you a new extreme in terms of the combinations, but it's showing you that there is the potential for life the moment this liquid comes about to use the water and come back to life. Put all this together, you're seeing that these new extremes that we found are still really far away from Mars-like conditions. And in fact, if we just look at the theoretical lower temperature limit for life of 233 Kelvin, if you compare it then to the lowest temperature a stable brine on Mars could have, we're talking about 225 Kelvin. Or sorry, the maximum temperature a stable brine on Mars could have is 225 Kelvin. That is still far lower than the lowest temperature that we have or that we think life would be happy with. So it's looking like things might be a little too rough for Mars in terms of the surface, in terms of what that could mean for a habitable environment. But I started this talk with caveats, and I want to end the talk with caveats, because science always has caveats along with it. That's what leads us to new discoveries, because caveats are really just future works. So in this talk, we've assumed that kinetics are instantaneous, but like I had mentioned, these processes can take a little bit longer, and that's what gets you into the metastable regions. We also assumed that all the water vapor could go into deliquescing a brine, right? And we also assumed that we know the limits of life, that we've actually explored all of these extreme environments on Earth. So for the kinetics part, one of the parts of future work that needs to occur is, so here And all of these pink dots, those are all of the different types of experiments we've done looking at deliquescence, adsorption, any experiment that was saying it was Mars relevant. I tried to grab all of the temperature and humidity conditions. And in this case, the cyan space here is bounded by the Phoenix and MSL data. So what you're seeing is that a bunch of the points are actually not at the appropriate combinations for Mars. Only a few of them are. So we need to actually start expanding our experimental capability to get into this region to better understand, can these processes occur on Mars? Can you have deliquescence on Mars? Because in fact, some of the experiments that are at the appropriate combination are showing that the kinetics to fully deliquesce might be just too slow. And so you might not be able to get a brine through deliquescence. The other thing is that because Mars is hyper-arid, we're competing for water, right? So maybe not all the water will go to deliquesce because it's getting absorbed or going somewhere else. But on the flip side, maybe adsorption in the regolith can create these niche environments like I mentioned at the beginning, where you suddenly are able to suck up enough water to create maybe a tiny little pore space somewhere where it's a little bit more humid than its surroundings. And so there, maybe you'll be able to deliquesce and form a more habitable liquid. And then, like I mentioned, just as I gave the example, just a few years after that paper came out saying this is the lower limit for life in terms of water activity, we found things surviving at far lower water activities. So who knows what we're next going to identify? So this might expand the regions that we think are actually habitable on Mars. In order to tackle that, what I've been working on is to develop a habitability metric that we can apply on Mars so we can compare and contrast environments. So in ecology, they use this thing called habitat suitability index models, which the USDA actually started off with so they could help farmers and everybody else compare and contrast different environments and say whether one was more suitable to this life that they're considering. It could also look at, so what I've actually done with it with my partner, who's an entomologist, we use those indexes to understand the ability of an environment to recruit. So that means the spread of an organism. In this case, we were looking at Japanese beetles and how they were spreading across the United States to be able to tell people, okay, farmers up here, or down here, you don't need to care about Japanese beetles, they might not get to you. But also that paper actually turned out to also allow us to predict how many Japanese beetles would emerge in the summer to help farmers understand how much pesticides they needed to put together. So we're using that framework, but I'm taking that over to Mars so we can start comparing and contrasting environments and say, okay, maybe this one is more habitable than this other relative to Mars. So with all of that put together and the caveats I mentioned, I'm gonna say thank you. That's my talk. Salty water everywhere, like I mentioned, well, not literally everywhere, but in a lot of places, but maybe you can't drink any of it. With that, I'm gonna say muchas gracias.